Okay, welcome to chapter 7. Um, we're going to talk about chemical reactions and chemical quantities. So, here we go. All right, I'm actually going to briefly skip over this and let's talk about chemical and physical changes. All right, so what is a physical change? Physical change is when we have an alteration of appearance. It can be a change of state, or it can be just simply color change or something along those lines. It does not change the identity, though, of what we're talking about. So, for example, water is an ice cube, is still H2O as it is a liquid that you drink. It's still H2O. Those are physical changes. Chemical change, that is when we do alter what we have. So we're going to start with one thing and end with something different. So to have a chemical change, you're going to have some rearranging of molecules, and so your reactants are going to be different than your products. Okay, so when we have a chemical change, there's a chemical reaction that occurs. And so when we write out our chemical reaction, we're going to start with our reactants, which you'll see on this side, and then we're going to make our products. So we're going to start with one type of thing. It could be several different molecules, doesn't have to be just one. And then you're going to end up with some different products. For example, here I have methane. It reacts with oxygen and it produces carbon dioxide and water. Our reactants are here and our products are here. You'll notice that in our chemical reaction, though, we have the same number of each one of them, each element. So I have one carbon here, I have one carbon here. I have 4 hydrogens, I have 4 hydrogens here. So the number of each thing you have, that's not going to change. It's going to be rearranged to change the identity of what the actual compound is. Okay, when we write our chemical equations, it gives us information about our reactants and our products, so we need to know the molecular or ionic formulas of them. We need to show what the state is. Is it a solid, liquid, gas, or is it aqueous? Aqueous, here you'll see is AQ. That just means it's dissolved in water. And we will use that quite a bit, especially in chapter 8. We'll need to know how many products and reactants we have, and we're going to do that by using what we call stoichiometry, or balancing our chemical equations. So let's go back to that methane. Here, the methane and oxygen reaction. So you'll see here, if I were to read this how it's written, I would say I have 1 mole of methane that reacts with 2 moles of oxygen. It produces 1 mole of carbon dioxide and 2 moles of water. So if I don't have what's called a coefficient right here, so if I don't see anything, that just means that there's 1 of them. And we say that is 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water. Now, this relationship, these numbers here, the 1, 2, 1, 2, those are called coefficients. And their relationship is what we know as stoichiometry. Stoichiometry tells us the mole-to-mole relationship of how many products and reactants we have. Okay, so we're going to look at balancing one. Let's look at this problem right here. So we're going to look at the combustion of butane. So butane, they give us is C4H10. Combustion reactions, if you remember this, but it's always reacts with O2. and our products are always carbon dioxide and water. Okay. Now, we're going to balance this and look at our stoichiometric coefficients. So the way we're going to do this is I'm going to start with carbon. I have 4 carbons here. So that means I need 4 on this side. And right here, I only see 1. So what I'm going to do is put a 4 here. Now that 4 does distribute to both of these, but right now I have 4 carbons and 4 carbons. Okay, so the carbons are good. Now I have hydrogen. How many hydrogens do I have? I have 10. So if I have 10 on this side, I need 10 on this side. I have 2 here. What can I put here in order to make that hydrogen 10? Because I have 2, what times 2 equals 10? It's 5. Okay, so again, it distributes. So now I have 5 times 2 is 10. I have 10 hydrogens. I have 10 hydrogens. All right, so my carbons are done, my hydrogens are done. Now I need to do my oxygens. So I have oxygen in 2 places here. 4 times 2 is 8, so 8 there. And then 5 times 1 is 5. So that gives me 13. 13 is a tough number to work with because it's odd, and we want these to be whole numbers. So when I have something like that, I'm going to make a change, because if I have 13 on my product side, it means I need 13 on my reactant side, and I can't take a whole number, put it here, multiply it by 2 and get 13. So when you, when you have something like this, what we're going to do is double our starting point. This one's not as neat. Okay, so what I mean by that is here, I'm going to double this and see if this won't make a difference. Okay, so how many carbons do I have? I have 2 times 4 is 8. I have 1 here, so I'm going to make this an 8. And I have 8 carbons, 8 carbons. So put our hydrogens next. 2 times 10 is 20. So I need 20 here. So I'm going to put a 10. 10 times 2 is 20. Right, now we're going to look at our oxygens. I have 8 times 2, that's 16. Plus 10 times 1, so that's 10. So I have 26 oxygens on this side. So I can make this 26 by putting a 13 there. And now it's balanced. One thing you should always notice is that your coefficients should never be divisible by something. So I can't divide all of this by 2, and that's because of this. But you shouldn't be able to divide it. Okay. Let's see. Sorry about that. Here. All right. So now we're going to look at balancing equations with some more ionic compounds in it. Okay. So here you would be able to write this out. So it says write a balanced equation for the reaction between aqueous strontium chloride and aqueous lithium phosphate to form strontium phosphate, solid, and aqueous lithium chloride. So let's start here. Aqueous strontium chloride, that's this. And the AQ just means it's dissolved in water. And then aqueous lithium phosphate, okay, here, strontium phosphate, solid, and lithium chloride, aqueous. So knowing how to put your compounds together is vital. If you don't know how to do that, you're not going to be able to write out your equations or balance correctly. So before we move forward, I want to talk about the polyatomic ions. Here, right, we have these parentheses. So as our coefficients distribute, so do these. So if it's outside the parenthesis, I actually have two phosphates, two phosphoruses and 8 oxygen. So they distribute just like a coefficient would. So we're going to go ahead and I always start from the beginning. So let's look at strontium. How many strontiums? I have 1. I have 3 here. So I need to put a 3 in front of this strontium. So now I have 3 strontiums, 3 strontiums. Okay. Next, I'm going to look at lithium. I have 3 lithiums here. Okay. I have 1 here. So I need to put a 3 here. And I see that. All right. So I have 3 lithiums, 3 lithiums. So here's where we're at now. We've balanced the strontiums and we've balanced the lithiums. Right. Next, sometimes you can look at the polyatomic ions as a whole. Not always, but when you can, it's the first thing I would look at, looking at it as a whole. But I have 2 phosphates. How many phosphates do I have here? Just 1. So if I do that, I need to put a 2 here. So you see that? I put the 2 there. Now, I have changed my lithiums. So we need to be cognizant of that. We have how many lithiums now? I have 6. 2 times 3 is 6. Where I had made it 3 here, but I can easily put a 6 here to rebalance those out. Then my last step, I've done the strontiums, lithiums, phosphate. So now let's look at our chloride. I have 3 times 2, 6 chlorides, and with my 6 here, I have 6 chlorides as well. So I'm balanced. I have everything right. All right, so why is it important? It tells us the mole-to-mole ratio of what we need in order to have a chemical reaction. It tells us, like, for example, here I have a combustion reaction, and this is for every 2 moles of this, I'm going to form 16 moles of carbon dioxide. For every 25 moles of oxygen that reacts, I'm going to form 18 moles of water. So we can use these ratios to compare and look at what we start with, what we're going to end up with. And this mole-to-mole ratio is going to be very important. I'll give you a real-life example. Real-life example here is that, let's say, for example, we want to make a pizza, and we need 3 things. We need a crust, we need 5 ounces of tomato sauce, 2 cups of cheese, and that gives us our pizza. So this is our reactants, and the pizza is our product. Well, let's say, for example, I have 6 cups of cheese, and I have enough of everything else. How many pizzas can I make? Well, we know just by looking at it, right, that we know that we can make 3 pizzas if we have 6 cups of cheese, but we can use this ratio. And the ratio is, for every 2 cups of cheese, I have 1 pizza. So I'm going to take the 6 cups I have and multiply it by that ratio. We're going to set it up as a conversion factor. 1 pizza for every 2 cups of cheese. So 6 times 1 divided by 2 will give me 3 pizzas. Now the cheese will go on the bottom because we want to cancel that out and go to our pizza. So looking back at that first one we looked at, we're going to use this mole-to-mole conversion, or our coefficients, to convert between 2 different parts of our reaction. Okay. For example, here I have the balanced equation. Now, if I want to look here and here, so let's say I'm given that I have 22 moles of this, and I want to know how much carbon dioxide is formed. Well, I'm going to take those 2, look at their ratio. It's 2 moles to 16 moles. I'm going to start with what I'm given. If the calculation is how much carbon dioxide will form if I start with 22 moles of C8H18. I'm going to start with what I'm given and then multiply it by the ratio being 16 to 2. It's really important to write your units here because you want to make sure that whatever you're solving for is on top and whatever you need to cancel out is on bottom. So we'll set this up in that dimensional analysis way. So if I react 22 moles of C8H18, I will form 176 moles of carbon dioxide. Now, if I want to find how much of a product I'm forming given a certain amount of reactant, or it could be vice versa, but you're going from one compound to the next. So you need a balanced equation, but to do the conversion, it has to be in moles, because the only way you can relate your reactants and your products is that mole to mole ratio. So if I'm starting, let's say that I'm given grams of my reactant and I want to know grams of my product. Well, I can do that, but the first thing I need to do is go from grams to moles. So grams to moles of whatever I'm starting with, and then I'm going to use the ratio to go to whatever I'm looking for in moles, and then I can convert that to grams. Okay, so here we go. Let's look at this. Actually here. Right, I'm going to set this up and then look at the next slide that will look a little bit prettier. But let's look here. Determine the mass. So I want to know the grams of CO2 produced. So I'm looking for grams of CO2 when 3.6 times 10 to the 15th grams of my starting compound is burnt or reacts. So here I'm going to go from the grams given of my reactant, and then I want to get to grams of carbon dioxide. But again, you can only go from one compound to the next in moles. So I'm going to have to go to moles of this before I can switch my compound. Okay. Once I'm in moles of this, then I can go to moles of, in this case, I'm looking for carbon dioxide. Okay. And then I can simply go to grams of carbon dioxide. The setup is going to be the same pretty much every time. So from grams to moles, we use the molar mass. From moles to moles, we use the coefficients from the balanced equation. And then from moles to grams, we use the molar mass. So you will have to calculate the molar mass of this and the molar mass of carbon dioxide. So this is what it's going to look like in fancier terms. I mean, in terms of it's written better. So again, I start with my grams of what I'm given. I'm going to convert that to moles using the molar mass. Then, and now we want to make sure that our molar mass here is going to be 1 mole over the mass that you've calculated, because your grams want to cancel. Now I'm in moles here, and now I want to go to moles of carbon dioxide. And I'm going to use that stoichiometric ratio, which I know from the balanced equation is 2 to 16. So I want these moles to cancel, so we need to make sure that C8H18 is on the bottom. And then I have put my 16 moles here. Then I can convert the moles of carbon dioxide to grams of carbon dioxide using the molar mass of carbon dioxide. So these moles should cancel. You should write this out every single time to make sure that you have these set up right and that what's canceling should be canceling. And that way it's a whole lot less room for error. All right, so here we go. Here we have a balanced equation. And we are given a problem that says, suppose you determine that a particular plant consumes 37.8 grams of carbon dioxide. So it's starting, I'm going to lose 37.8 grams of this. Assuming that there is enough water, what mass of glucose, so I want to know what mass of glucose of this here will be formed from this being consumed. So I want to go from grams of carbon dioxide to grams of glucose. So same pattern. We're going to go from grams of carbon dioxide to moles of carbon dioxide, from moles of carbon dioxide to moles of glucose, and then from moles of glucose to grams of glucose. All right, so we've given that. We're looking for grams of glucose. So we're going to make our pattern again. So it's going to be the same conceptual plan. We're going to go from grams of CO2 to moles of CO2. And how are we going to do that? We're going to use the molar mass of CO2. 1 mole of CO2 is 44 grams. Then we're going to go from moles of CO2 to moles of glucose using that mole to mole ratio, which you're going to get right here. There's 6 moles of CO2 to 1 mole of glucose. Then we're going to go from moles of glucose to grams of glucose using the molar mass of glucose, which you would have calculated. All right, so let's see. Here are the relationships that we just went over. And so we're going to start with our CO2, what we're given. We're going to multiply it by the molar mass ratio. Those grams are canceling. Then we're going to go from moles of CO2 to moles of glucose, cancel out the moles of CO2, moles of glucose to grams of glucose using the molar mass, and cancel those moles out. So if 37.8 grams of CO2 reacts, 25.8 grams of glucose will be formed. Let's do one more right now. All right, so here we go. We have 25 grams of sulfur dioxide. And so the question is, if 25 kilograms of sulfur dioxide were to react, what mass of sulfuric acid will form in kilograms? Okay, so same steps here, except we have one additional one. We're going to have to go from kilograms to grams in order to use the molar mass. All right, so we're given, we always start with what we're given, and then we need to find a product. So we're going to have this standard format. We're going to go from our mass to moles, moles to moles, moles to mass. Our mass is in kilograms, so we're going to convert that to grams first. All right, so here's our conceptual plan. This is what we're given to start with. Kilograms of sulfur dioxide, we're going to go to grams. We know that ratio. Then we'll go to moles using the molar mass of sulfur dioxide. Then moles of sulfur dioxide to moles of sulfuric acid. And then to grams of sulfuric acid using the molar mass. And then we can convert back to kilograms. So here's our conceptual plan. Now let's put it together. Okay. And so following that, we have this set up right here. Kilograms to grams, make sure these cancel. Grams to moles using the molar mass, these need to cancel. Moles to moles from sulfur dioxide to sulfuric acid, these should cancel. And then I can end up getting to my kilograms of sulfuric acid.